Hello, welcome to Talks at Google this afternoon. My name is Rob Leeworthy, and I'm absolutely delighted today to welcome Kat Arney. Dr. Kat Arney is an award-winning science writer and broadcaster. She was a key part of the science communications team at Cancer Research UK for more than a decade, co-founding the charity's award-winning science blog and acting as principal media spokesperson. Kat holds a PhD in developmental genetics from Cambridge and is the author of two previous books, How to Code a Human and Herding Hemingway's Cats. Kat will be talking through her new book for around 40 minutes before we take questions, so please do use the live chat window for that. And so without further ado, please welcome Kat Arney.
Hello, thank you so much for having me. It's
welcome
an
to Google.
Joy. Yeah, hello, and hi to everyone, all you Googlers. Thank you for spending time with me this morning.
Well, look, we'll chat again in around 40 minutes or so, but please do tell us about your new book. We're very excited.
Thank you very much. So yeah, I'm going to talk to you about my new book, which is, ta-da, Rebel Cell, Cancer Evolution and the Science of Life, available now in the UK and coming out in the US towards the end of October. Alas, the print run was a victim of COVID-19, so we're all a little bit delayed there. But I'm going to talk to you about some of the themes in the book that sort of help to explain why I think this is a new way of thinking about cancer. This is not entirely my way of thinking about cancer. This is sort of an emerging idea around thinking of cancer as an evolutionary disease, almost as a disease of the ecology of the body. And it's a kind of way of thinking about this disease that has been emerging over recent decades, but I think is only now starting to gather momentum and come to the fore. And I think it's an incredibly powerful way of thinking about a very ancient disease. And I think it's potentially the way we need to think about it if we're going to make substantially more progress in the future. So let me get my slides. So, where am I? So when we're thinking about cancer, I'm going to cover three main areas. So where did cancer come from? What makes it so difficult to treat? And how can we beat it? So thinking about some new strategies based on this evolutionary thinking. Now, before I start, I really want to stress that we have made progress in cancer, and absolutely significant progress. So right now, certainly in the UK, the glass is half full. Half of all people diagnosed with cancer will survive for 10 years or more after their diagnosis. And that's a figure that has doubled even within my own lifetime. So, you know, the glass is half full. We have made significant progress. But I think that unless we can really change how we think about cancer, particularly treating advanced cancers, we're not going to fill that glass to the top. So the first idea that I really wanted to tackle in the book was really wanting to address this myth that some people have that cancer is a modern human disease. It's weirdly persistent, this idea that it's just humans that get cancer and it's just the fault of our modern, toxic, terrible lifestyles. And, you know, I knew that this wasn't true when I started researching the book, but I didn't realize quite how wrong it was, because cancer has always been with us. It is a disease that we find across almost every single branch of the tree of life. Wherever you look, you find examples of cancer. So we can find cancers in reptiles, in amphibians, in birds, in bats. We can find evidence in dinosaurs. So the week that my book came out in the UK, there was a story about a 77-million-year-old dinosaur fossil that had been found with an osteosarcoma, a bone tumor. So this is a disease that is widespread across life and deep in evolutionary time. I think the oldest fossil I found was there's a 240-million-year-old proto-turtle fossil that has a tumor in it. So this is not purely a human disease, and it's not a new disease. And one of the examples that really struck me, this was a research study published in 2014. And this is the creature on the right that you can see. This is a hydra. This is a tiny, tiny organism that is little more than a tube of cells with tentacles on top. They live in the water. And in 2014, some researchers discovered a tumor that had naturally grown in one of these creatures. So they hadn't induced it or done anything funny to it. This was a naturally occurring tumor in an organism that is absolutely tiny and is literally just 3 types of cells. So this really dispels the myth that somehow cancer is purely the domain of humans, purely a modern phenomenon. It goes deep back into time. and it goes deep across the tree of life. There are two really notable exceptions, which are very, very interesting. So comb jellyfish apparently do not get cancer. No one knows why. What's the deal with the jellyfish? And also sponges. So there's a researcher in Arizona State University, Carlo Maley, he's studying these tiny little sponges. He's zapping them with more radiation than would kill a human, trying to give them cancer. And these sponges are just fine. So again, sponges, very, very interesting organisms that seem to be resistant to cancer. And one of the books I drew on when I was researching Rebel Cell is a new book by Beata Ujvari and her colleagues, compiled by them. It's The Ecology and Evolution of Cancer. And it's fascinating. In here, they have pages and pages of tiny type of all the animal species that they found examples, documented examples of cancer. You know, everything from boomslang snakes through to green iguanas, through to hyenas, shell ducks, ostriches. If you can imagine it, unfortunately, it can get cancer. So it's not a new disease, and it's not a purely human disease. So as I said, there's evidence that dinosaurs get cancer. And in fact, the more we look, the more we find. So, you know, researchers who are studying ancient fossils don't go around looking for cancers in these fossils. So the first study of dinosaurs and cancer was done by someone going around all the museums in North America with a scanner and saying, can I pop your dinosaurs in the scanner? And found evidence of tumors, particularly in duck-billed dinosaurs called hadrosaurs. So they seem to have been, you know, proportionally a slightly more cancer-prone species. But again, as I say, this is not a new disease. And everywhere we look in human populations, ancient remains, we find evidence of cancer. There's more than 250 documented examples that we can pretty much say, yes, that was a cancer in an ancient human population all over the world. There are children's tumors, there are adult tumors. So this is a disease that has always been with us. And the more we look for it in ancient life, the more we find. And the thing that I realized as I was writing the book, that the reason why is because cancer is the price of multicellularity. So where I kind of really start from in the book is I start from the origins of multicellular life 4 billion years ago. One cell becomes many cells. But originally, every cell was separate, unicellular organisms, bacteria just doing their own thing. But as multicellular life evolved, cells came together. And when you start living together as cells, there are things you gain and there are things you lose, as in any society. So you lose your independence, you lose your freedom, you lose your, I'm just going to do me, it's all my own thing. But you gain the ability to be bigger, to eat more, to be faster, to move around, to exploit new niches. So there are many advantages to being multicellular. And this is why multicellular life has evolved. But at the same time, we know that once you have a society, there can be cheats. And that's a really interesting idea that it's been around for quite a long time. I think, you know, for decades, this idea that our tissues are a cellular society and that to be a healthy society, cells should not reproduce too much. They should clean up behind themselves. They should do the jobs they're meant to be doing. They should be gone when they're no longer needed and not pollute the environment around them, not take more than they need. This is what keeps our tissues healthy. As long as all our cells are more or less doing that, we will have healthy bodies. And the new exciting idea in cancer, this is particularly work of a woman called Athena Tippis at Arizona State University. She's someone who studies animal societies, human societies. And she realized that our tissues are a cellular society and cancer cells emerge as cheats within that society. They take more than they need. They reproduce more than they should. They stop doing what they're meant to be doing and they go and do other things. If every cell did that, our bodies really wouldn't work at all. You'd sort of have this Mad Max dystopia. But cheats can prosper. And it's a new way of thinking about cancer as almost the inevitable emergent property of multicellular tissue. As soon as you have cells that have picked up changes and can be different from the cells around them, they have the capacity to cheat if their changes have enabled them to do that. So this idea that cancer is the price we pay for multicellularity. If we're going to be multicellular, if we're going to have our cells behaving in the cellular society, we have to accept that cheating cells can emerge. Now, this sort of raises some interesting thoughts about, like, well, are you saying that if you lived your entire life completely healthily, if you did nothing that we know increases the risk of cancer, yeah, this means that there is a chance that you could develop cancer. There are still things we know increase the risk of that happening. So we know that there are things that damage our DNA, that encourage cells to become cheats. We know that there are things that disrupt the environment of the tissue, make it a bit more of a lawless state where cheats are more likely to emerge. But at some really deep point, cancer is the price we pay for life. So for me, I find that quite a reassuring message, because I think sometimes we can be told that it must have been something you'd done. What did you do? What caused it? Was it your fault? We want something to blame for cancer. And ultimately, the thing we can blame is that we are incredibly, wonderfully evolved multicellular beings. And at some level, deep level, the emergence of cancer is almost an inevitability. And here, this was one of my late night thoughts, after a couple of scotches, was like, given that we find cancer across all of life, all of multicellular life, we can find evidence of cancer emerging. If there were multicellular aliens, would they have cancer? And I think probably the answer is probably yes. If they're multicellular organisms, and if they obey the rules of evolution by natural selection, then probably yeah. So that's maybe one for you guys to argue about later in your kind of beer time. So when I was at Cancer Research UK, I'd spend a lot of time writing articles that started like, "What is cancer?" And we have this idea of cancer. They'd always start the same. They'd say, cancer starts when a cell picks up genetic mutations and multiplies out of control. And I sort of call this like the genetic bingo theory of cancer. It's more formally called the somatic mutation theory. And it's this idea that cancers emerge when a cell has picked up enough genetic changes in the right genes. It's ticked off its genetic bingo card to enable it to go out of control and go down the road to becoming a tumor, to becoming a cancer, multiplying out of control, not dying when it should, doing all the bad stuff that we know that cancer cells do, spreading around the body, all of that kind of thing. And that sort of fits with the idea of cells as a society. You've got cells, they've picked up genetic changes. This enables them to be cheats. And I was all like, okay, yeah, I can really get with that. This is how we connect our understanding of the genetics of cancer into our understanding of the cellular society and the emergence of cancer out of our tissues. So it's like, well, that's great. But there's a problem, because that view of cancer, purely based on the fact that you have faulty cells that have genetic changes, and that's the thing that's absolutely responsible for these cancer cells, that relies on all the other cells being normal. And I think we're a little bit guilty as scientists sometimes of only studying the things that are wrong. So for a long time, people have only looked at samples of cancer to look at the genetic changes, to look at the mutations and say, like, what's gone wrong? What can we find that's faulty or mutated in this cancer sample? That must be what's caused this cancer. This must be what's driving the cancer. And no one really thought to really look at healthy tissue. And it's only in recent years that we've actually had the technology to do deep genome sequencing on tiny, tiny patches of tissue. And it's become cheap enough to do this on normal tissue as well. Why would you study normal tissue if you're trying to study cancer, right? So it's a bit of a flip in mindset. But a team of researchers at the Sanger Institute, led by Phil Jones, Inigo Martin-Carreno, and Peter Campbell, they said, like, well, yeah, let's look at normal tissue, because we have this idea that cancers are full of genetic changes, full of mutations, and that's what's driving cancer. So, well, let's just check out some normal cells. And so the first experiment they did was to take little patches of skin from the eye. So some people, you can get sort of a problem where the skin of your eyelid becomes very droopy and it can interfere with your vision. So it's a small cosmetic procedure to remove this little sort of wing-shaped piece of skin. And normally that would just be thrown in the bin. So they spoke to some surgeons in the local hospital in Cambridge and said, can we get your scrappy bits of skin? And they were like, yes, and consented the patients. Were like, well, I don't need it anymore, so go for it. And they took these small pieces of skin and cut them into tiny, tiny, tiny pieces and did deep genome sequencing on them. And they discovered that even this apparently completely normal looking skin, there's nothing that looks wrong with this skin. These patients don't have cancer or anything. This is normal, healthy skin. It's a patchwork of mutation. There are all sorts of different little patches of cells with all sorts of different mutations, some of which, if we found them in a cancer, we would say that is a cancer gene. That is a cancer mutation that is driving this cancer. So that was revelatory. That was the first time that someone had done such an in-depth study of normal tissue and found the true extent of mutation within it. And then they went on to look at esophageal tissue. So this is the esophagus that connects your mouth to your stomach. And they expected to find mutations in skin because it's exposed to ultraviolet light, which we know causes mutations. They didn't expect to find so many mutations in the esophagus because, it's on the inside, I guess. But it was incredibly surprising. So these diagrams, they represent, each little circle represents a patch of tissue with specific genetic mutations in it. And the different colors are the different genetic mutations. And they looked at people in their 20s, people in their 50s, people in their 70s. And you can see by the time you get to middle age, you are a patchwork of mutation. By the time you're in your 70s, there's a lot of stuff going on. Your cells have seen some things. And again, these are mutations, many of which, if we found them in a cancer, we would say that is a cancer driver mutation. And these were perfectly healthy people. They had no signs of cancer at all. Their esophageal tissue was healthy. So since then, there's been more studies done, looking at things like blood, looking at the endometrium. By the time a woman reaches her 60s, most of the endometrium, the lining of the womb, is made up of mutated cells, but is not cancer. So we need to really rethink this simplistic idea that a cancer is basically just a little pocket of genetically mutated cells. There's something more complicated going on. So what can we say? Well, this is really interesting because, all your cells have seen some stuff by the time you get to a certain age. You are a patchwork of mutation. And again, like I say, many of these mutations are what we would call cancer mutations. But cancer is incredibly rare. Now, this is a bit of a controversial statement because on a population level, cancer is incredibly common. We know from statistics tell us that now 1 in 2 people alive now are likely to be diagnosed with cancer at some point in their lifetime. That is incredibly common. But on a personal level, individual to you, you are made of trillions of cells that multiply millions, billions of times in your lifetime. You are full of mutations. And yet each one of us may only get 1, maybe 2 individual cancers, new cancers, in our entire lifetime. So on this personal cellular level, cancer is actually incredibly rare. So there must be some very, very special events that enable cells to emerge out of this kind of general melee of mutation and really start going for it. And I think that's important to remember as well, that most of the time our bodies do an amazing job of dealing with the hurly-burly of life, of suppressing these rogue and damaged cells, of keeping us healthy well into old age for many of us. And it's interesting because we only really study why we get sick. We don't study why we stay well. We don't study what makes healthy tissue. There's something really incredibly suppressive against cancer about our tissues through most of our lives. The risk of cancer only really starts going up when we get to our 60s. And in the book, I sort of explore some of the evolutionary reasons for that. But something is uniquely suppressive in our bodies as we're younger against this kind of this cheating, the emergence of these rogue cheating cells. Where are we? Here we go. So then the big question is, if all our cells are a bit sad if all of them have got mutations in them, what actually turns a sad cell into a bad cell? What enables a cell to take that leap from being just a sort of a mutated cell, expanding, growing into this little clump of mutated cells, into a cancer? What is that quantum leap? Now, what I'm showing you here are human chromosomes. This is called a karyotype. These are the 23 pairs of normal human chromosomes. So, they all look fine. We've got 23 pairs. They match. Beautiful. Next, I'm going to show you some chromosomes from different breast cancers. And these are aggressive breast cancers. And I hope the difference should be obvious to you. So what it seems, and this is increasingly being shown in research, that it's not just about single mutations in single genes. The thing that turns these sad cells into bad cells seems to be some kind of chromosomal catastrophe. Chromosomes being doubled, chromosomes being lost, chromosomes being cut and pasted around the place. We don't exactly know why that happens. Some of this is a phenomenon called aneuploidy. We know there may be some things that encourage it, some things that discourage it. And I do talk a bit about that in the book. But at some level, this is not just a disease of faulty genes. This is a disease of faulty chromosomes. Some big bad stuff is going on at some kind of tipping point that turns cells carrying mutations into cancer cells. So I think this is a really exciting idea to be looking at, is about what triggers this chromosomal catastrophe. There's a lovely word for it's called chromothripsis, which basically means chromosomes being shattered. And we can see evidence of whole chromosomes being completely smashed up, stitched back together in all kinds of ways. What causes that? That seems to be a real kind of fuel for evolutionary processes that, it sort of mixes everything up. It shuffles the deck of the genome in these cells and allows them to really start changing and really going for it. So, these kind of messed up chromosomes, not just the genes, but the sort of the whole chromosomal fuel for evolution is basically rocket fuel. I kind of describe cancer as basically a bin fire of evolution, or a dumpster fire for the US listeners. You've got a whole mess of stuff in there. Cells are trying stuff out. They're evolving. They're being selected for in the environment they find themselves in. And all this genetic change is rich, rich fuel for evolution. But at the same time, as we're starting to discover this, the way we think about treating cancer is incredibly focused on these single genes. It's incredibly targeted. So since we've had the evolution of genome sequencing and being able to take samples of tumors, mash them all up, sequence the genes, look for the mutations, find what we consider to be cancer drivers. So mutations, molecular changes that we think are driving the cancer cells to grow. And here is just a sample of them. We find the genes in the cancers, and then we develop the drugs, the magic bullets that target them. And this is an approach that's been used. Really, the poster child for this is a drug called Gleevec, which was developed for a certain type of leukemia, chronic leukemia. And it targets a particular faulty molecule that's made when two genes kind of get glued together. Shouldn't normally live together, but they get glued together. They create this faulty molecule that drives the blood cells to proliferate. And Gleevec locks into that faulty molecule, stops it from working, cancer cells stop growing. Gleevec, I think, is arguably the most successful targeted cancer drug of all time. And it kind of misled us into thinking that if we could just find the mutations, find these faulty molecules, and develop more and more and more drugs for them, we would be able to treat all cancers. And that approach has really been followed, I think, for the past couple of decades, with some success, but in many cases with really, I think, marginal gains. And the problem is this. So this is an image that in the world of cancer research is quite famous. This is someone with metastatic melanoma. This is skin cancer that has spread all through his body. It's a very distressing picture to look at, I'm aware, and I apologize, probably should have warned people. It's going to be showing some medical images. But we can see that the tumors have spread through his body. And this person was given a drug called vemurafenib, which is specifically designed to target one of these faulty molecules in cancer cells. And it appears to have absolutely incredible effects. So after just 15 weeks on this treatment, this is the same patient. I was at a cancer conference when these results were presented, and you could hear in the room people just like, wow, because this looks incredible. This looks like the miracle cure for cancer that we've been searching for. This looks like a wonder drug. It's amazing. The problem is the next picture, which is just 8 weeks after that. And the drug, it worked incredibly well. But the problem is that cancers, just as our normal tissues are a patchwork of mutation, cancers are a patchwork of mutation. And by the time a cancer has got to a certain size and spread to a certain amount, there are going to be cells in there that carry genetic changes that make them resistant to almost any treatment you can throw at them. And so this is why we see with these very targeted therapies, they seem to work incredibly well. And then the cancer comes back, because somewhere in there are going to be cells that are resistant to the drug. And once all their buddies around them have been killed, they can start growing again. And this is responsible for the absolute heart-sinking phenomenon that I'm sure many of us will know, where someone has been treated successfully for cancer, and then after weeks, after months, in some cases after years, the cancer comes back. And, this sort of leads us to this way of thinking about using these new drugs in a way that I describe in the book as kind of whack-a-mole. And, it can really work. And there's a friend of mine who's now 4 years into his diagnosis with stage 4 metastatic bladder cancer. And he was never expected to survive that long. But, he's taking a treatment. Eventually, his cancer starts growing again. And there's another treatment that's now available that he can try. So it's kind of this whack-a-mole idea that try one drug, when it stops working, try another drug. But at some point, you are out of options. And that is not good enough. And in some cases, these drugs are incredibly expensive. And the gains that they bring in lifespan can be measured in weeks or months. In one paper, I saw 9 days benefit of survival. And these drugs bring in millions of pounds if they can just get over the line and show that they are slightly more effective than another treatment. It unlocks an enormous market, but really for marginal gains in survival. These are not the cures, the miracle drugs, the game changers, the holy grails that the headlines would have us believe. And, I spent a long time working for Cancer Research UK. I'm not a kind of tinfoil hat-wearing pharma conspiracist kind of person. The pharmaceutical industry is the way that we turn science into life-saving drugs. But what I would question is the incentives to develop drugs that really genuinely prolong life. Maybe we can use these drugs in different ways. And there's a lot of excitement about using combinations of therapies, sort of hit them with one, hit them with another. You're less likely to evolve resistance to 2 drugs or 3 drugs. But the toxicities add up. So, there's only so much chemistry that a human body can take. There's also a lot of excitement about immunotherapies. These are treatments that harness the power of the immune system to unleash the immune system upon cancer cells. But they don't work for everyone, and we don't quite know why. And in some cases, they can actually cause what's called hyperprogression. So, the immune system is an incredibly powerful beast, and we need to be very careful how we wake it against cancer. So that is a very exciting idea. But generally, I think this just fixation on finding targeted therapies in really quite a narrow range of targets, that the number of targets that we currently focus on to find cancer drugs is incredibly small. So, we're just looking in one place for just one type of approach. And I think unless we can really start to broaden our horizons, we're only going to continue to make really marginal gains with that kind of approach. So here's the question: how can we really win against cancer, and particularly these advanced cancers that are evolving, that become resistant to therapy, that we currently really struggle to treat? And so talking to people for the book, one of the areas that really excites me is using evolutionary ideas, ecological ideas, to not just use new drugs, but even use the treatments we have in a much, much cleverer way to try and make a bigger impact. And one of the leaders, I think, in this field is this chap. This is Bob Gattenby. He is absolute superstar, really great person. He's at the Moffitt Cancer Center down in Tampa in Florida. And he is using his weapon in the war on cancer is maths. And you can tell he's a mathematician because he's got a blackboard. So everything is covered in chalk in there. But yeah, Bob is using mathematical approaches based on population mathematics, understanding populations of cells, how they change, how we can balance them out, to actually understand what is going on as cancers evolve resistance, merging the genetic data we have with this understanding from an evolutionary perspective of growing and shrinking populations, of resistance, of sensitivity to drugs. How can we treat cancer more effectively? And he's very into ideas like game theory, so trying different approaches, different gambits to try and kind of steer the evolution of cancer down the roads that we want. And there's a lovely scene in the book where I basically chase him around his office playing a Stackelberg game, for those of you who are into game theory. And I win by using a dustbin. So it's worth reading the book just for that alone. But his idea is something called adaptive therapy. So this is one of the approaches that he's tested so far in a clinical trial. And the idea for this is basically comes out of things like the way that farmers manage pests. So the assumption when farmers have crop pests is that you can't get rid of every single beetle in your crop. You just can't do it. The damage that you would inflict on your crops, or the time and the effort that you would spend, is just not worth it. So you accept that there's going to be a certain level of beetles that you think is acceptable. And also within that population, there are going to be some beetles that are resistant to the pesticide that you put on them. There'll be some that will be sensitive and will be killed by it, but some that will be resistant. But the important thing is that being resistant to pesticides actually incurs a kind of a fitness penalty. So if you're a beetle that is resistant to pesticide, you're actually less fit. You're a less good beetle. And so normally the beetles that are sensitive to the drugs, to the pesticides, they kind of keep the resistant beetles in check. What you don't want to do is get rid of all the sensitive beetles, because then the resistant ones will just go, woohoo, grow everywhere. And then you can't use that same pesticide to treat them. And Bob realized, this is exactly how we treat cancer. We have a way of treating cancer with what we call the maximum tolerated dose, the MTD. And this is literally, MTD means as much dose as you can give a patient. And so we give big doses of cancer drugs, of chemotherapy, of these targeted drugs. And it gets rid of the purple cells in this diagram are the cells that are sensitive to the drug. But remember what I said, that in a cancer, once it gets to a certain size, there will be cells in there that are resistant to any drug you can throw at it. So there will be resistant cells in there. So you get rid of all the sensitive ones. You're left with pretty much just the resistant ones. They're tiny. Maybe it's a tiny population. Maybe you can hardly see them, but they will be there. And then you treat again because you're like, woohoo, this is working. Let's do it again. Let's do it again. And all you're doing is selecting for those resistant cells. So this is a big problem, and this is why cancers come back. If you want to blame something for this, you blame Charles Darwin. This is just evolution in action. We're imposing a selective pressure on a genetically different population. And the idea of adaptive therapy is, again, you assume that there are sensitive cells and you assume that there are resistant cells. And also you have to know that your drug-sensitive cells can grow faster, they are fitter than the drug-resistant cells. And the idea is also you need to have some way of measuring the burden, the absolute volume of tumor cells that you have in the body, like how much cancer is in there, how many cells have you got? And you start treating with a drug. You wait for that cancer to shrink to a certain size, maybe halfway. And so you know that in there you've got sensitive cells, you've got resistant cells, are kind of muddling along. and then you stop treating. And the sensitive cells will grow back, but they're keeping the resistant cells in check. And you wait for the cancer to grow back, and then you treat again. And you just repeat these cycles. And it's very, very counterintuitive, because normally when we treat cancer, we want to get rid of it. That's the idea, get rid of it. And this is about kind of riding a roller coaster of balancing these populations of resistant cells, of sensitive cells. And they've tested it so far in a trial in prostate cancer, initially because it's very easy to measure the burden of prostate cancer within the body. You can do a simple urine test called the PSA test. But they've increased survival without progression on this treatment from an average of 18 months to 4 years. So normally people with advanced stage prostate cancer, once they start taking this particular drug, it would get them going through 18 months before their cancer grew back and was then untreatable. On this therapy, they have people who've been on it for 4 years before the cancer does come back, because inevitably that population of resistant cells will grow, but it's been kept in check for so much longer. I cannot stress enough how excited I was when I first learned about this, because if this was a drug, people would be falling over themselves. But it's just using a therapy that we already have, that it's already authorized for use in prostate cancer. It's just using it in a different way. And there's other trials ongoing in different types of cancer. The key thing is you have to be able to monitor that burden of cancer within the body. And like I say, with this kind of roller coaster approach, resistance does eventually emerge. You know, the sensitive cells can't keep the resistant cells in check forever. So we need some alternative ideas. We need to think about, this way round is about controlling the cancer, trying to control that evolutionary journey for as long as possible, balancing the populations of cells, making them fight it out against each other. But it's not a cure. And what we all want for cancer is cures. So if we can think of strategies that are more clever, even with the treatments that we already have, then we stop thinking maybe about cure. And with our evolutionary ecological hat on, we start thinking about extinction, because that's what we're really talking about. If we're talking about cells as populations living in environments with selective pressures, we can see examples of this in the natural world in populations of animal species, and we're very good as humans at driving animal species to extinction. So how can we learn from extinction events to actually break this population of cells down and down and down and down to the point where it's not sustainable? So one example from the natural world that Bob likes to use is the heath hen. So this is a heath hen. Heath hens were around in the for many, many hundreds of years in the US, particularly up the eastern seaboard of the US. And when the European colonists arrived, they were like, woohoo, enormous, great big birds, very tasty, absolutely hunted them to bits. I mean, there's actually one of the stories goes that the original Thanksgiving turkey was in fact a heath hen. It kind of looks, they're about kind of turkey sized, but they were hunted almost to the point of collapse. So it was a tiny population. And by the sort of the 19th century, there was a tiny population of heath hens, the last population left, just living on Martha's Vineyard. Their habitat was shrinking. More and more buildings were being built there. Their habitat was shrinking down and down and down. So they got down to a very small breeding population. There's very low genetic diversity. And that's a problem, because you just don't have enough genetic fuel to try out things to get you out of the evolutionary hole that you're in. Genetic diversity is good for evolution. You've got lots of species, lots of organisms that can try different stuff to get out of it. There was a fire on their breeding ground. There were several harsh winters, and finally a disease just wiped them out. And the last heath hen died in 1932. It was a heath hen. He was so rare that he had a name. He was called Booming Ben. So the last heath hen finally went extinct. And we can tell these extinction stories for many, many other organisms, because we have driven many organisms extinct on this planet. Many of them have gone extinct under their own, under the things that have happened to them, environmental catastrophes, diseases, shrinking habitats, predation, all kinds of things that happen to species to drive them extinct. So what can we learn from this about treating cancer? Well, in fact, we have already learned some of these lessons by accident in the way that we currently treat children with leukemia, because this was entirely worked out by trial and error. But there's certain combinations of drugs that have different actions given at different times that eventually add up to a disastrous impact on the population of cancer cells within the body and drive it extinct. And back in the 1940s, survival from childhood leukemia was, fewer than 1 in 20 children. It was effectively a fatal disease. And today, more than 9 in 10 children will survive leukemia, will go on to live long and happy lives. And that's an extinction strategy. And there are some ideas of how to do this with adult cancers, with more advanced cancers. I was talking to a researcher who's working in melanoma, and she's trying to use some of these targeted therapies, some of these immunotherapies actually, in the right way before surgery to kind of act as a sort of a catastrophic impact. And she's starting to see some really interesting results there. So I think just thinking more strategically about how do we actually accept that there are going to be all kinds of cells in a cancer with resistance and sensitivity and on their own evolutionary journeys. How do we try and steer evolution in the direction we want, whether that is to control or ultimately to extinction, if that is possible? And when I went to talk to Peter Campbell at the Sanger Institute, he's one of the UK's leading cancer genetics researchers, I did ask him, like, well, where does this get us to? If this is the idea, if we are trying to control cancer, maybe drive it to extinction, everyone does have to die of something. And he was like, well, yeah, I mean, the end game of this research is that we can all live long enough to die of something else first. And I personally would very much like to see a world where no one before their time loses their life to cancer. I think it's just such an incredibly destructive, painful disease. It steals the people that we love from us. And I would really like us to see where, we can live long, happy, healthy lives for as long as we wish for. And also writing this book, I think cancer is a word that strikes a lot of fear into us. It's a scary disease. It's incredibly scary. It has always been one of humanity's, I think, deepest fears. But writing this book, really understanding what this is as a disease, understanding, what the statistics are, what the odds are, where the research needs to go. I took a lot of reassurance from this quote from Marie Curie, who said, "Nothing in life is to be feared. It is only to be understood." And Glenn Seaborg sort of quoted that and said, "Now is the time to understand more so that we may fear less." And I really think just being honest about what cancer actually is. It is an evolving system within the ecology of the body. It's not just a clump of genetically mutated cells that we can just fire magic bullets at. We can no more stop a cancer with a magic bullet than we can stop a hurricane with a shotgun. It's a system. It's an evolving system. And we need to accept it as that, and we need to understand it as that, and we need to treat it as that if we're to fill that half full glass all the way up to the top. So I will end there, and thank you very, very much for your attention.
Thank you, Kat. So if you have any questions, please put them in the live chat. I have a couple. Let's have a great chat. We've got about 15 minutes or so. So Kat, thank you again. A really brilliant talk. I've learned so much. I suppose the first thing that jumps to mind is cancer is both this very personal issue to patients and those of the patient's loved ones, but also a societal issue that we talk about, the war on cancer and these big terms that we align cancer almost with terrorism and drugs and so forth. How do you think society should be viewing cancer? What's the narrative shift that we need to do to get away from Daily Mail headlines and big headlines?
Yeah, this is a really challenging one because, the famous one is Nixon declaring war on cancer, which it didn't work out so well. So this was, Nixon was looking for something after the Apollo moon project. It's like, I need something really big. Like, I need my Apollo. And it's like stuck in the mire of the Vietnam War and it just needed something. So it's like, we're going to declare war on cancer. And, within a decade and, by the early 80s, it was like, this isn't happening. And it sort of, I think, really fueled a lot of almost conspiracy thinking about like no one's really making any effort, no one's doing this in the right way. It turns out like you can't declare war on a biological concept. Like, you know, as I really explain in the book, this is a disease of multicellularity and evolution. And like, you can't declare war on multicellularity. Like if you want to not ever have cancer, you've basically got to be an amoeba, and, you know, or not have evolution. And so we can't declare war on this. We will never, ever live in a world where cancer does not exist, because we are living multicellular beings that obey the rules of natural selection, evolution by natural selection. And I think something else that has been really challenging, and it's very interesting as someone who worked for a cancer charity, is this narrative of the cure. So we have been driven by, you know, since Cancer Research UK was set up in the early 1900s, this narrative of finding the cure. And this idea that the cure for cancer is a drug, one treatment, one thing. And for a start, cancer is not one disease. Almost every individual person's cancer is a unique one-off evolutionary event. You know, it evolves within you, your unique body, your unique genetics, and it goes off on its own choose your own adventure evolutionary trajectory. So this idea that there's going to be one treatment that's going to work for everything is absolute frank nonsense. But this concept of the cure has really obsessed us. And also then when you start to talk about the idea that evolutionary strategies that are designed around long-term control for years, potentially decades, and people are like, well, that's not a cure. I want a cure. I want this cancer to be gone. And psychologically for patients as well, you know, talking about the adaptive therapy trial, that kind of roller coaster, it's hard to ask patients to stop taking a drug that looks like it's working and say, okay, we're going to stop and we're going to wait for your cancer to come back, and then we're going to treat you again and it's going to work again. And they're like, really? I really hope you're right. And the first time Bob talked to me about the first time that they rode that cycle, and he was like, I really hope we're doing the right thing here. And it turned out that they were. And actually one patient on the trial said, you know, my cancer's shrinking. I just want to keep carrying on the drug. And, you know, fairly predictably, he did end up passing away remarkably quickly because, you know, that's the resistant cells came back. So this idea of like, what is the cure? What does it look like? So I'll just quickly read. There's a very sniffy editorial in the Times that there was a Centre for Cancer Evolution launched here in the UK at the Institute for Cancer Research. And the editorial in the Times said, you know, if the slogan for these charities were like, together we will delay cancer, would you have raised enough money to fund research into 200 different types of cancer? Almost certainly not.
Yeah.
So as society, but I think we need to stop asking for the cure because it doesn't exist. So let's start asking for smarter, more effective treatments.
Great. Thank you. We have a question from Benny. So I've heard an idea that cancer should be thought of as an immune disease occurring when the immune system fails to identify and clean up cancerous cells. Is this a useful way to think about cancer?
Yes and no. So I more think that cancer is a tissue disease. So I talk a lot in the book about the idea of the society of cells and sort of the ecology, the landscape of cancer in the tissue. And immune cells are, of course, a really important part of all our tissues. All the tissues of your body are just riven with immune cells. They are all over the place. And they're inside a lot of cancers too. There are regions in cancers that are immune hot with loads of immune cells that we can think of as almost like predators picking off cancer cells, and there are regions that are immune cold that kind of shun immune cells and get rid of them. So yeah, ultimately, cancer does grow because it has evaded the immune system. The immune system hasn't recognized and got rid of it. We know that probably the immune system all the time is clearing out damaged and faulty cells before they can even get a foothold. And we do see some successes from immunotherapies that kind of unmask cancer to the immune system. So yeah, I think viewing it partly as an immune disease and partly as a tissue disease, I think is a new way of thinking about it. And yeah, the power of the immune system, I think we're really only just starting to tap that.
Great, thank you. We have a comment from Linda. So I'm paranoid about toxins, pesticides, plastics. After hearing your talk, it seems there's really no way to prevent cancer, even if all plastics and pesticides were eliminated and all we ate were greens. Obviously, greens help the fight against, bowel cancer and so forth. Do you worry about toxins, pesticides, plastics? all these things?
I mean, I am a human living on planet Earth. I've only got a limited time and brain capacity to worry about everything without going mad. So I'm very selective in the things that I worry about. I will say, so I've had a few people when I've been talking about the book, they've said like, so basically you're saying I should just not bother. I should just go down the shop, like just buy a packet of cigarettes. It just doesn't matter what you do. And like, no, because we do know if we start thinking about this idea that like cancer cells, what makes a cancer cell is cells that are managing to emerge out of the system of the tissue. And that tells us two things. So we do know that cancer cells do have genetic mutations. They do have this chromosomal chaos within them. And we know that there are things that encourage that. So things like cigarette smoking, toxins, X-rays, UV light from the sun, nasty chemicals. These all do add to your mutational burden. So yes, of course, don't do things that add to your mutational burden. If you're going to be a human living in the world, there's only so many things you can absolutely avoid. But like avoid deliberately adding to your mutational burden, I would say. But also we know that this is also about the health of the tissue as well. So again, something like smoking actually causes tissue damage. It causes inflammation. We need to understand a lot more about how do we keep our tissues healthy? So what does exercise actually do for our tissue physiology? That's not really clear. And we know exercise is very protective against cancer and lots of other diseases. We don't really know why. So how is it keeping our tissue healthy? How is things like obesity actually increasing inflammation within the body? And inflammation, I think, it kind of comes back to the idea of the cancer is almost an immune disease. Like inflammation, I think, is a key driver of tissue damage that enables rogue cells to emerge. So, I certainly try not to worry about too many things in my life. Otherwise, I'm going to go mad. I try to not increase my mutational burden. I try to do the things that we know help to keep us healthy. But at a certain level, and I do talk quite a bit in the book about this sort of idea of like bad luck and all that kind of stuff, like inherently, we are a cancer-prone species. So even if you lived a perfect, blameless life, there would be a risk that a cancer would emerge. And also, ultimately, we can never show what fired that fatal bullet, know, and made it happen. So life is ultimately for living and for enjoying is also my philosophy.
But more generally, we should eat well, we should take exercise, we should sleep as much as we, get
we
some
know
great
all
sleep.
Those things reduce the risk of cancer. What's interesting is how, and can we actually enhance that, I think is an interesting question.
Well, perhaps related to this with diet, Michael has a question. I'm curious to hear your opinion on a ketogenic diet. Is that pronounced correctly? As a cancer treatment, is there a basis for it? Should we think of it as another tool in a multifaceted approach?
Yeah, so for those people who don't really know, there's lots and lots of interest in manipulating people's diets as a way of sort of manipulating the environment within the body. The problem is that, to some extent, yes, cancer is a systemic disease. Cancers exist within the system of the body. They can access the nutrients that you put into your body. They can access the blood and the lymph and the oxygen and everything that's going into your body. Like they are part of us. With diets and things like that, I think there's a lot more that we need to know. And also really highlighting that even the studies that have been done show very different impacts for different people and different cancers. Again, this comes back to there's no one way. We need to understand what someone's individual cancer is like. You hear a lot of stuff about like, oh, you should like starve it of nutrients or not have any sugar. And, it's like, well, is that actually the right approach for this individual's cancer? And in some cases, actually, if you look at the examples from ecology, where you have species that are starving, they will start migrating more in search of more food. So you want to be really careful when you're thinking about strategies that do manipulate nutrients and all these kind of stuff, because you don't know what impact that is going to have. And also there's a sort of tangentially related, there's a lot of interest in like, oh, can you manipulate the pH of the body and all this sort of pH diets? It's like, you can't, because you have kidneys and they're really, really good at maintaining your pH. But like down on a very local level, the local sort of environment of a tumor, yes, is acidic. So I think there's some interesting stuff there about like, how can we manipulate the very, very local tumor environment? But that probably is going to be very difficult to do if you're trying to manipulate the entire environment of the body, because that's very resistant to changing.
Well, let's pick up on kind of manipulating in various things. Let's take Claudio's question. when he asks about clinical trials. So a typical clinical trial is long and complex, test one drug and one regime. How would you go about testing many more regimes? Do you see a role for technology in this?
Oh, hell yeah. And you should go and talk to the guys.
Scientific method at its heart, yeah.
You should go and talk to the guys at the Moffitt if you're interested in this. So there's a whole breed now of mathematical biologists that are really doing the hardcore modeling on this. So taking the genetic data, taking the evolutionary data and the mathematical modeling to really understand this, and like building models of cancer. So you can go, all right, if we have this population of cells and this population of cells in an in silico model, and we apply this drug or this pressure and that pressure, what's the outcome going to be? And they're called like, I've heard people refer to like phase I trials for in silico. So before you even get to a human trial, you've actually run a trial in silico, effectively. Okay. Yeah, it's super cool stuff. Like this whole meeting of mathematical biology and cancer biology is very exciting. But it is a problem, and it's a regulatory problem for the drugs themselves, because you normally do only get authorization to use one drug at a time. So coming with these rational strategies, particularly these kind of rational extinction combinations, is going to need a real shift in the regulatory agencies in how we think about testing drugs. And I think I would like to see more expansion of this kind of in silico modeling, because also like I think like the animal testing isn't, animals are not really a great model for human cancers. That's a tangent, but like this more of this in silico testing and then taking it into trials so you can go, yes, this rationally devised strategy actually works.
Great, thank you. Well, look, we've got time for one more question, which I will take. How the book is out there? We could talk about launching a book of pandemic. I think more pressing though. I can imagine. How would you like the book to be received by patients? At the end of the day, it's a human disease, cancer, or at least for us, it's not a human disease. We've covered that. But how would you like the book to be received by patients?
Yeah, it's really hard writing this, because you're obviously aware that patients are going to read this, people going through cancer, people's families. It's a very hard book to write. I have friends, I have family going and have been through cancer, and we've all lost people that we love to this. And some of it is a hopeful message. I write at the beginning, this isn't a book about cancer, it's a book about life. And I want this to be a book really placing this disease in the context of life, and mostly how amazing our bodies are. But yeah, I think it is a bit challenging in some places where you're saying like some of the directions that we're looking for treatments, and maybe the things you've been told about the direction in which we're looking for treatments maybe is just very narrow, and we need to expand our horizons into a new way of thinking about cancer. And a new way of thinking about how we treat particularly advanced cancer. We're very, very good at treating early stage cancers. And certainly I would not want anyone to read this book and go like, I'm not going to take my doctor's advice. I'm not going to do any treatment, because doctors are working with the absolute best information that we have right now. But I think painting the picture of where the future should be going is really what I'm trying to do here.
Great. Well, thank you so much. The book is available in the UK now. You've narrated the audiobook, haven't you?
I did do the audiobook. So if you love my voice, you can get 9 hours of it.
And it's released in the US on the 13th of October.
Maybe the 20th of October.
Mid-October, set up your...
to late October. It's available to pre-order now from rebelcellbook.com, and you can buy the UK copy as well.
Perfect. So, well, look, on behalf of everyone dialing in and who will watch it in the future, Kat, thank you so much for joining us at Talks to Google today.
Thank you very much. It's been a pleasure.